The two designs that we looked at were the simplest kind of designs you can have, where you have two factors A and B. A is from a completely randomized design on the whole plots, and factor B is a randomized complete block design on the subplots. But we can handle more complicated split plot designs. And what it's going to look like, for an example, is, again, split plot designs are essentially combining two different experiments into one. So, for instance, you can have a two-way completely randomized design for the whole plot and a one-way randomized complete block design for the subplot. Let's say an agricultural company wants to know what type of supplements A1 and A2 and diet B1, B2, B3 when given to a cow would produce the largest calves after a year. If that was all they were interested in, we'd have a two-way completely randomized design if they just picked out a single calf from the cow and weighed it after a year. If they took four calves, weighed them after a year from each of these cows, that would be a completely randomized design with subsampling. But to add in a little extra twist, what ends up happening is to make the design a little more complicated. Four calves from each mother are randomly selected and given a different dose of a growth stimulant. So four calves taken from the mother, given a different one of four doses of the growth stimulant. If we were just looking at the growth stimulant, this would be a randomized complete block design, where we're treating the mother as a block and the calves as our experimental unit. So we have one experiment that's done on the 30 cows, and we'll have 5 cows per treatment combination. That means we have a two-way completely randomized design with 5 replicates. The reason why we have 5 replicates are there are a total of 30 cows. Factor A has 2 levels because of the 2 supplements. Factor B has 3 levels for the 3 different diets. 2 times 3 gives you 6. 30 total cows in a balanced design would be 30 divided by 6, or 5 replicates. And then another experiment is conducted on the 4 calves taken from their mothers. In this case then, we'd have a one-way randomized complete block design because we were looking at the growth supplements given to the calves, and that'll end up having a total of 30 blocks, one for each mother cow. But we're combining the two together, so what we'll do is we'll have YIJKL. Y is the weight of a calf after a year. I is going to be the effect of the supplement given to the mother. J is going to be the effect of the diet given to the mother. K is going to be the effect of the supplement, the growth hormone, given to the calf. And then L is going to be the cow from the ith-J treatment combination. So I is going to go from 1 to 2 for our 2 different supplements. J is going to go 1, 2, and 3 for our 3 different diets that the mother cows can get. K goes from 1 through 4 for the 4 different doses of the growth stimulant. And L, we have our 5 cows per IJ combination. There are a total of 30 cows, but L by itself will go just from 1 through 5. And we can write out the model in terms of our 2 pieces. For the experiment done on the 30 cows, for our two-way completely randomized design, we'll just write out a two-way complete randomized design. Alpha I plus beta J plus their interaction plus the error term from the replicates themselves. So we have the effect of the supplement, the diet, the interaction term between supplement and diet, and then the elf cow in the ith-J diet supplement combination. So this would be our model if we were just looking at our two-way completely randomized design. Adding in a randomized complete block design for the growth hormone given to the calves from the mothers, this would be our effect of the block. Then we have our treatment effect for the growth hormone given, the interaction terms between supplement and hormone, the interaction term between diet and hormone, and then the three-way interaction term, plus the error terms that come from the calves themselves. Mentioned in the first video, the interaction term goes in the lowest level that a particular factor appears in. That's also in that interaction term. So for instance, the interaction term for alpha and beta Since alpha and beta are both in the whole plot, the interaction term is in the whole plot. However, alpha and gamma, alpha's whole plot, but gamma is subplot, so the interaction term belongs in the subplot part of our model. Beta and gamma, for the same reason, belongs in the subplot. Alpha, beta, gamma belongs in the subplot. It just takes one of them, one of the interaction terms, to be in the subplot for the whole interaction term to be in the subplot. Alpha's whole plot, gamma subplot, alpha-gamma interaction, subplot. We can make our design even more complicated. Let's say that the agricultural company in the previous example conducts the experiment on 6 different farms. Now what we can do is we can treat these 6 farms as blocks. So everything else is the same, but instead of just doing it on a single farm, we're doing it on 6 farms. That means the whole plot experiment also becomes a randomized complete block design if we're going to treat these farms as blocks. Now we have y, I, j, k, l, m. I is going to be the factor A, j is factor B, k is factor C, L is going to be the farm, and then M is going to be the cow from that farm treatment combination. So this will end up being our 2A randomized complete block design part. H is going to be the random effect from the farm. Alpha, beta are our 2 whole plot factors. Alpha, beta, I, j is the interaction term for the whole plot factors. D is going to be the effect of the mth cow with the under factor A, its ith level, factor B's jth level from farm L. And then the second part, we also have our subsampling, because we have this error term would also be included since we have those 4 calves. Again, if we were just looking at 1 calf, this would be our whole model. If we're looking at 4 calves per cow, then we have the subsampling part down here, the error terms for the individual calves as well. This part down here, since we haven't done anything new to the calves themselves, that part essentially stays the same, where we have a randomized complete block design for the subplot plus some extra interaction terms thrown in. The main takeaway from this idea of these split plot designs is they're not just limited to 2 factors, a whole plot factor and a subplot factor. The whole plot factor has to be a completely randomized design, and the subplot factor has to be a randomized complete block design. We could have reversed this around. We could have 1 whole plot factor and 2 subplot factors if the diet were given to the 4 calves instead of the mothers. Then we could have done a randomized complete block design with 2 factors. And this would be a randomized complete block design with 1 factor if we're still considering these 6 farms. These split plot designs can get really complicated because essentially, again, they're just a combination of 2 experiments done simultaneously.